Next up, we'll hear from Jared Males about next generation instrumentation GMagAO-X.
Thanks, Vanessa. Can you hear me okay? Yep. Okay, good. So the problem we're trying to solve here is captured by these two plots where I've taken the confirmed planet sample and plotted it as mass versus separation normalized by luminosity, or radius versus effective temperature. And in purple, you see the exoplanets where we have taken an image or a spectrum of, and in green, where we have a transmission spectrum of it. So this is sort of my attempt to capture what the population of planets that we have characterized. And you'll see that they're either close or far away, or they're hot and big. And conspicuously on this plot is there's this big gap right in the temperate zone. This gray bar is the habitable zone. And so this is the gap we're trying to fill in with our future direct imaging instruments. But to be able to do this, we have to build an instrument that can be not dependent on the age of the planet and not dependent on orbital alignment. And we have to get very close to the star. And astrophysically, that means 50 milliarc seconds or closer is where this starts to get interesting. And this is all pushing us towards working in reflected light. And this is just an example of some work that Logan Pierce did to try to help us design an instrument to do this. And it's just showing if you have a visible color magnitude diagram or visible near IR, can you distinguish between different models of Proxima b, whether it has an atmosphere or whether you're just looking at mud. And all of this is pushing us towards needing extremely high contrast. So this is showing 10 to the minus 7 in here, and this is lambda over d units, 800 nanometers and 25 meter diameter telescope. So 5 here is about 30 milliarc seconds. So we need extreme contrast very close to the star in a visible near infrared high contrast imaging if we're going to be able to fill in this gap in the known planets that we're not yet characterizing. So this means we need to solve this problem we all have with speckles inside 3 lambda over d. And this is sort of an aspirational physics-based illustration, not really representative of any instrument, but it shows this is just a standard AO loop closing, and then we're going to put in an ideal coronagraph. So this is excellent wavefront control, no non-common path aberrations. Still can't see these fake planets that I've injected. And then we're going to turn on optimal AO control. This is predictive control. Now you can see one of these little planets dancing around there because the speckles got fainter and faster. And then finally, the next breakthrough we need is PSF-based, or telemetry-based PSF subtraction. Because at these separations, ADI is not going to work, SDI is not going to work. We're going to have to use our instrument telemetry to be able to reconstruct this speckle pattern and dig out those planets. The key thing is none of this actually really works on sky yet. So we have a lot of work to do on current generation instruments to make this theory into practice and prove that we can do this with the ELTs. I'll take a second and just watch the video run one more time. So there's that, you can pick out that planet now, and then when we turn on this telemetry-based PSF subtraction, even at a few lambda over d, we'll be able to dig out these faint sources. So that brings us to GMagAO-X, which is our current extreme AO system on the Magellan Clay Telescope. It's a 2,000 actuator, 3 kilohertz AO system. We have a coronagraph with its own AO system. We have a separate DM and a suite of wavefront sensors running in the coronagraph. And from the beginning, when we started in about 2019, this has always been our test bed for GMagAO-X. So this has been how we've been testing our designs and ideas for how we're going to build this instrument for GMagAO-X. This is a nice gallery of some results that we've gotten to date. We're doing everything from searching for new white dwarf companions, doing circumstellar disk imaging. You'll see we work all the way down to G-band, so this is a total intensity image of HR 4796. These are conventional sort of young giant planets, but in the visible. So there's Wysis 1b. There's a poster on that, Beta Pic B in the visible. And then Laird's coming next, so I'll let him tell you all about the exciting H alpha results. But I'll just put a plug for Jaolin's poster. We're also doing lots of instrumentation research, high-order control loop optimization. So Rico Lammen has a nice poster up about his neural network control of the pyramid sensor. It's reconstruction. The key thing there is it lets us stop modulating, so we go from this PSF to this PSF on a 7th magnitude star. It's a big improvement. If we want to do any of this quantitative stuff with wavefront sensor telemetry, we have to have it calibrated. Eden has a poster about measuring the optical gain effect on the pyramid sensor, a very nasty problem. Everything has to work perfectly, so Katie has a poster about our closed loop atmospheric dispersion correction. And we got to get smart about using all the information we have. So Parker has been climbing all over the telescope, installing accelerometers, and you can go see his poster about how we're fusing all of those all those signals together. And of course, we're working really hard on coronagraphy and post-AO wavefront control. EFC is now basically almost a routine part of our operations, so you can use EFC anytime you want on GMagAO-X. And we're seeing factors of better than 10 improvements in raw contrast from that. We're also working really hard on small angle coronagraphy. We have a demonstration of PSEMC on Sky. Go see Elena's poster for that. And this all comes together with a bunch of advances in low order wavefront sensing and control, PIA fabrication research. Joseph had a great poster on telemetry-based PSF subtraction that hopefully you saw. Miles is working on polarimetry. And tomorrow, Josh is going to tell you about our efforts towards the SEC on GMagAO-X. So the big lesson we've learned from trying all this stuff on Sky is that Strel ratio really matters. And that sounds sort of like a tautology, right? Like, no kidding, you want good wavefront control. But there's sort of this second order effect where all of this focal plane wavefront sensing and post-AO stuff goes nonlinear. And that happens at even like 0.65 arcsecond seeing. And so to do that, we think to be able to implement all of these control loops and keep these this design working, we need a really high actuator count DM so that we can maintain that flat wavefront. So we have a solution. This is the Giant Magellan Telescope. It's 25 meters across, being made out of 7 8-meter segments. If you're an AO scientist and you look at this, you're like, well, why don't I just use a bunch of DMs and put one on each one of those segments? And that is our solution. We have created what Laird has dubbed the parallel deformable mirror. And so here you'll see the GMT pupil, the 7 segments here, going into this beam splitter. And what it does is it disassembles the GMT pupil, images each segment on its own 3000 actuator MEMS DM, and then reassembles the pupil. And we've demonstrated that we can at least do imaging with this system in the lab. So here's Alex and Maggie aligning the prototype parallel DM. So this is 21,000 actuators. This is equivalent to a 184 by 184 DM, which you can't buy today, but you can make one. Putting on my project management hat, this is maybe the key thing right here, is that we can place a PO for these devices today. I have this non-functional one sitting on my desk at home. So this is a big deal for developing this. Of course, you have to keep it in phase. Go see Maggie's poster to understand what we're doing. To keep the telescope in phase, this just illustrates the problem behind the coronagraph if we have a little bit of phase error. We have done a lot of lab work to demonstrate that we can do this, that we have the sensing and control strategies to keep the GMT in phase. So all this leads us to GMagAO-X. So this is our design for this instrument for the GMT. It sits here below the primary mirror on a rotating platform that also tips with the telescope. And this is what it looks like. We're building our own tertiary mirror, some 4 optics, and then it goes into this rotating barrel. I'll highlight that these 2 electronics cabinets are almost all DM electronics. So that's what happens when you have 21,000 actuators. So our science cases are kind of what you would expect. The big one is we want to do reflected light imaging of nearby known planets. So we're just using the RV catalog here and potentially search them for life. And then these other ones you can sort of summarize as today's direct imaging better. Right? So we're going to take advantage of the D to the 4th sensitivity scaling and do young giant planets. We're going to do H-alpha, better disk images, and stellar evolution is pretty interesting. At this spatial resolution and spectral resolution, I think we're going to learn some pretty interesting things about stars. So here's a visual representation of our high-level contrast spec. So we need to get to 10 to the minus 7 at 4 lambda over D on the GMT. And that 4 lambda over D is that's sort of important number because that's outside the diffraction pattern of a single segment. So if we can't control phase well enough to keep it well in phase, that's sort of what our inner limit will be. So that's the risk management there. What we're actually going for is 2 lambda over D and down to 10 to the minus 8 is the target that we're designing to. And of course, we'd really like to get that deep, but that's starting to get pretty hard. High-level view of the instrument parameters. Just really pay attention to the middle column because that's what we're designing to. So we're going to work from R band to H band. In our G band, sorry, that's G band, we'll have 4 milliarcsecond resolution. And we're aiming for up to R of 100,000. Small field of view, that's really a consequence of that pupil splitting that happens at the DM in double pass, so that constrains our field of view quite a bit. But it doesn't matter because I'm talking about working at 50 milliarcseconds, so this is more than I care about anyway. This is what the instrument looks like. So it's a 2-level optical table, which is just like GMagAO-X. Here, the high-order AO system is on the lower level, and you can see that parallel DM just barely fitting in there. And then on the upper level is where the coronagraph is, and there's a periscope connecting them. A key feature here is that it's floating on air. So this is just like an optical table that you would find in a lab floating on air with an active leveling system so that it keeps us aligned. The scary part about that is the telescope tips over. And so if the telescope tips over while we're floating, the whole instrument will just slide down. And so as a consequence of that, we're rotating our optical bench. Image rotators aren't that scary. We do it all the time, but not really with coronagraphs like this. And so the key thing here is that this, if you concentrate on this section back here, which is the actual AO system and coronagraph, as we tip over, the whole thing rotates so that it stays up and down. Minimizes flexure, lets us be on that floating optical tables to stay vibration isolated from the rest of the telescope. One important point is that we're just not worried about the GMT aperture. It's a pretty complex aperture, but at the raw contrast levels we need to deliver for a ground-based instrument, modern coronagraph design techniques are having no trouble handling this. This is a broadband designed by Sebastian using the PAPLC, the phase apodized pupil Leo coronagraph. And we're also have PSCMC designs that also perform pretty well. So this is where we are now. Probably the big announcement as an update to this talk, if you've seen it before, is that we're now an official GMT instrument that's been fast-tracked for first light. We're in the project baseline. Our final design is funded. I have an email waiting for me about negotiating a contract when I'm done with this talk. And we're aiming to have FDR done about a year from now. So the punchline here is, this is where I started. These are the exoplanets that we can't characterize. And if GMagAO-X works to spec, this is the number of planets that we're going to be able to characterize their atmospheres, color-coded by host spectral type. And it's really going to have a significant improvement in our ability to do this. You see a bunch of temperate giant planets around solar-type stars, and of course the terrestrial planets around M stars down here. So here's a nice shot of some of our group on an observing run, and a shout out to our sponsors, and I'm happy to take any questions.
Thank you so much for a really interesting talk. This is Jules Fowler from UC Santa Cruz. It's always really cool to see the design with the 1 DM per segment. I was wondering, as you're thinking about control strategies, are you planning something that's like one big controller that treats all of the DMs like one big DM? Or are you thinking you'll be running like each DM per segment as its own little control loop?
Yeah, it's a good question. So for the low order stuff, I mean, it's a single optical system, right? So you got to control the whole thing. From a practical matrix math perspective, the 3,000 segments are easier. Like, think about splitting it onto different GPUs and stuff like that. The GMT does actually they have a Carhoonen-Levy basis on each segment that they control separately. So it's kind of an open question that probably comes down to things like the practicality of GPU memory and stuff like that.
Hi, Aniket Sanghi from Caltech. Great talk. I was curious, so GMagAO-X is a pathfinder to GMagAO-X. Are there any other technologies that are going to be demonstrated on GMagAO-X in preparation in maybe the upcoming years or so?
New technologies with GMagAO-X. Well, go to Josh's talk tomorrow, because we have demonstrated the self-current camera on Sky, but we have a new flavor of that coming. I think right now we have most of the stuff in place that we need. Now we just have to make it work. Probably the biggest push now is going to be on the PSF, telemetry PSF reconstruction, speckle reconstruction from telemetry.
It was an excellent talk. Jared, so my question is on predictive control. So the potential for it to get contrast is breathtaking, but on Sky right now we have substantially poor performance.
Yep.
What do you think is the path to improving the efficacy of predictive control, and how important is it to achieving your contrast goal?
Very good question. So it's very important. So we have some backup plans using high dispersion coronography, cross correlation kind of stuff. We're not focusing on that, but so with predictive control there are two things going on. So one, we don't know how to do the pseudo open loop reconstruction, and I think that's a major limit in a lot of what's preventing us from achieving the goals. That's related to the telemetry PSF subtraction. Like, we have to be able to calibrate our wavefront sensors. We have to be able to understand what the open loop wavefront is. There's a way around that. There's like the data-driven closed loop techniques. So I think that the two paths to making predictive control work better are solve the pseudo open loop reconstruction problem and/or develop closed loop predictive control and make it work on Sky. On GMagAO-X, the practicality is we are actually getting killed by actuator saturation. So when we turn on predictive control, it kind of works, but then it doesn't handle the stroke limits on our DM very well. And then, of course, yeah, sure, I'm over. Yep, got it.
Sorry.
I could go on about.
Obviously, lots to ask about GMT or GMagAO-X. So thanks for an inspiring talk, Jared, that brought forth a lot of questions.